Hi everybody. In today's lecture, I'd like to talk to you about SP hybridization and bonding orbitals for nanoscience. Now, this is important to understand so that you can understand especially some of the nanostructures of carbon and why they look the way that they do. So, to remind you, we talked about orbitals and the basic shapes of orbitals as solutions of the Schrödinger equation in an earlier lecture. So the Schrödinger equation can only be solved and predicted exactly for hydrogen, which has just one electron. And then from the solutions to that equation, we get the basic shapes of the orbitals. So for example, the 1s orbital is basically a sphere, and then the p orbitals look like kind of dumbbells or figure eights. Now other orbitals can have pretty crazy shapes. These are cross-sectional images of what they look like here. But even so, these are relatively simple pictures because they just have one electron in them. When you get multiple electrons in an atom, the picture changes a little bit. What happens is that the orbitals have a tendency to overlap with one another or hybridize. So let me explain. You have the s orbital, that's the solution for L equal to 0, ml equal to 0. And then of course, for each orbital, you can have a spin up and a spin down electron. So you can have two electrons, a pair of electrons in each orbital. So you have your spherical shape s orbitals that can hold two electrons, and then you have your dumbbell or kind of figure eight shaped p orbitals, right? The p orbitals have L equal to 1, and ml can be either 1, 0, or minus 1. And then the 1, 0, and minus 1, those can hold two electrons apiece. So there could be up to 6 different electrons in p orbitals in a full shell, okay? Now, according to a theory called the valence shell electron pair repulsion theory, what happens is these electron pairs in these orbitals, they repel one another. And the bond and the lone pairs around a central atom are generally separated by the largest possible angles possible, okay? Now, sometimes to meet the requirements, and also to form bonds, the orbitals will shift their shape a little bit. Now what will happen is the s and the p orbitals kind of merge to one lumpy sp orbital, okay? And this is hybridization. What will happen is that they'll form these lobes. You can see here that we have a 2s and then a 2pz merging to form this sp hybrid. And it's kind of this funky shape that has a big lobe to it and a little lobe to it, okay? Now what happens in hybridization is the little lobe, that stays around the host atom, and then the bigger lobe points towards the outside atom that it wants to bond to. And this ensures that you have electrons in orbitals in between the two atoms, and of course, if the electrons are in between the two atoms, then they do a better job of bonding or holding those atoms together. So it makes sense that the big lobe points towards the other atom so that the electrons spend more time there, right? Because a bigger cloud, more time, right? And then that means that the bond is stronger, okay? So let's focus in on carbon because we're going to talk about the nanostructures of carbon a lot. Now carbon has 6 electrons, and from your modern physics course, you could write out what the structure is of those electrons in their different energy levels. So you might say, okay, well, there's going to be 2 electrons in the 1s orbital and 2 electrons in the 2s orbital, and then that leaves just 2 electrons for the 2p orbital. And so you might draw it kind of like this, where the up and the down arrows, of course, represent the spin up and the spin down electrons. And so this would be what we would imagine that the energy level structure of carbon is. But what happens is carbon especially likes to undergo sp hybridization, which means that the s orbitals and the p orbitals, they're going to overlap. When they overlap, they're going to make new funny shapes, and those new shapes mean new energy levels. Now it turns out that those new energy levels are actually lower energy than before hybridization, and so hybridization is energetically favorable. And it also makes it easier to form those bonds because it forms the lobes with the big lobe and the little lobe, and the big lobe points towards the other atom, right? So there's different kinds of hybridization that carbon can undergo depending upon what kind of bond it's forming. So let's talk about diamond first. This is what the structure of diamond would look like with the ball and stick model. You can see that it's got this tetragonal kind of arrangement, right? Okay, so how does it form bonds that have this tetragonal structure? Well, that happens because the 2s and the 3 possible 2p orbitals, they fuse together and they make new SP2 hybrid orbitals, and they make 4 of them. So we envisioned the energy level structure of carbon as being like this, with 2 in the 1s, 2 in the 2s, and 2 in the 2p. But here's what it really looks like. There's 2 in the 1s, and then there's 4, 1 in each of these SP2 hybrid orbitals, right, that are formed when the s and the p overlap, forming 4 orbitals, okay? Now, those 4 unpaired electrons, they're each in their own little orbital there, they can now form 4 bonds with neighboring atoms, right? And so that's exactly what diamond's doing. Here's the carbon in the center, and it's got these 4 electrons that are forming bonds with each one of those neighbors as shown in the picture. This is a very strong, tightly bound arrangement, and diamond is actually one of the hardest materials known. So you can kind of picture and visualize what these hybridizations would look like by doing these demonstrations with balloons, okay? So if you think of the shape of the hybridized orbitals, or the arrangement of the hybridized orbitals, you can tie these balloons together, see, in the center by their stems, I guess, for lack of a better word. And this is kind of that tetragonal structure that we talked about. Now, these SP2 orbitals, these hybridized orbitals symbolized by these balloons here, they're oriented at a bond angle of 109.5 degrees from one another. In other words, as far from each other as they can get. And the balloons naturally form this shape when you tie them together. Now, it doesn't all have to be SP2 hybridization. You can also have SP2 hybridization, and that can help explain a trigonal planar structure of molecules like we see in graphite, and I'll show you that in just a second. In SP2 hybridization, what happens is you have your 2s orbitals and only 2 of the 2p orbitals hybridizing, and they form then 3 sp hybridized orbitals, okay? So that's shown here in this little image that I borrowed from Chemistry Libre text. Here's your 2s orbital, and it overlaps with, say, for example, the 2px and the 2py orbitals. The 2pz is left alone, okay? And then that forms these 3 kind of mushroom-shaped, if you will, SP2 hybrids, okay? And then this is kind of what it would look like. Again, the big lobe points towards the other atom so that it can form these nice, strong bonds. And then if you wanted to do this with balloons, this is what it would look like, this trigonal planar structure right here. And of course, in the balloon structure and in these images here, the unpaired, if you will, p orbital isn't shown, but it would stick up out of the plane. So, as an example of something that is undergoing SP2 hybridization in order to form bonds, you should think of graphite. This is a little image of a ball and stick model of graphite over here. And you can see that it forms this kind of hexagonal structure in a sheet. And then the sheets lay on top of one another, okay? Well, that hexagonal structure is a direct result of the trigonal planar geometry of the bonds. If you focus in on one of the bonds, you can see that it bonds to 3 nearest neighbors within the sheet. And then, of course, as it bonds together, it forms those little hexagons. Now, inside the sheet, you have a lot of strength. Those bonds are very strong, you know, just like the diamond bonds are very strong. But what happens is in between sheets, okay, there's very weak bonds holding the sheets together, just van der Waals bonds. And so this is the difference, right, in between diamond and graphite, okay? Diamond, one of the hardest materials known. Graphite is actually a lock lubricant, and we put it in pencil lead. So it scratches off very easily, leaving behind the pencil marks on your sheet, okay? You can also have sp hybridization, where you have the s orbital hybridizing with just one of the p orbitals, okay? And that leaves the 2 other p orbitals unchanged. Now in this figure here on the left, that's an example of sp hybridization. in this figure, it shows all three of the different hybridizations carbon can undergo here. And what you've got is in the orange in these figures, the orange are the hybridized orbitals, the SP hybridized orbitals, and then the purple are the unchanged p orbitals, okay? So here's the SP, right? Here's the SP2, and you can see the unchanged p orbital sticking up out of the plane. And then here's kind of the diamond structure with the SP3, where they're all hybridized. Okay, now here's some more technical jargon you might hear, and that's the idea of sigma and pi bond orbitals, okay? So sigma and pi bonds, those are what you get for chemical covalent bonds, okay? And sigma and pi bonds are caused by the overlap of the atomic orbitals that we've been discussing. So sigma bonds are when you have a head-on overlap of atomic orbitals. And they're strong. They're very strong bonds. And so that's kind of, you can visualize it here. These are the different kinds of sigma bonds that you can get. You can get SS, SPZ, and then so on and so forth. It just keeps going. But anyway, it's a head-on overlap. Pi bonds are a type of covalent bond formed by a sideways or lateral overlap of atomic orbitals. Okay? So to do this, I'd like to talk about ethylene, which is shown here. So ethylene is when you have two carbons that have a double bond in between them, and then 4 hydrogens attached there kind of at the corners like you see. Okay? So let's look at what's going on here. Okay? This is SP2 hybridization. Okay? So you've got that trigonal planar kind of geometry. All right? And so in between, there's a sigma bond in between these neighboring carbon atoms, and there's also sigma bonds in between the carbon and the hydrogens. All right, but because it's SP2 hybridization, there's that p orbital that's sticking up out of the plane, and that p orbital is still free to overlap with the p orbital in the neighboring carbon, and that's what happens. See, that pi bond then forms between that overlap of these p orbitals that are sticking up out of the plane. So you have the sigma bond in between the two carbon atoms, and you also have the pi bond that occurs up out of the plane, and that allows a double bond. Okay, so that's what's going on in ethylene. Now you can also have SP hybridization going on in, let's look at acetylene. Okay, so in SP hybridization, remember, you've got your S and one of the p orbitals combining, and then that leaves forming the SP hybrid orbital, leaving 2 remaining p orbitals that are free to form those pi bonds. Okay, so here is acetylene, right? And you have in this a triple bond in between the 2 carbon bonds. Now that's formed by a sigma bond, that's the head-on bond in between the 2 carbon atoms. That's pictured in green here. But then you can see the py and the pz orbitals are unchanged. They are not hybridized. So they're sticking up out of the plane like so. Well, when it gets close enough, right, when they get close enough together, those p orbitals will actually overlap, forming 2 pi bonds shown here. Okay? And so then you have the sigma bond and the 2 pi bonds forming the triple bond in between the 2 carbon atoms. Okay? And then, of course, you have the sigma bond in between the carbon and the hydrogen there on the left, and the carbon and the hydrogen on the right. All right? Okay, so that's kind of what's going on. So if you hear me talking about sigma bonds or pi bonds or SP hybridization, or you want to understand why carbon forms the crazy geometries that it does when it hooks up in all these interesting ways to form nanoparticles, then that's the basics of why. I hope you enjoyed it, and I'll see you in our next